Since the beginning of time, water has been used to put out fires and remains the most effective extinguishing agent. It is environmentally friendly, inexpensive, and in most cases readily available. Years of experience, technology innovation, and research have allowed us to put the bucket brigade days behind us and focus on modern tools and tactics to effectively cool surfaces and extinguish fire. Applying water to confine and extinguish fire is one of your primary fireground responsibilities. Utilizing different techniques and methods of water application based on your situation at hand will help maximize your strategic and tactical effectiveness. But before we get to discussing different suppression methods, it is important to discuss and understand the fundamentals of hose streams, specifically the concepts of air entrainment and water mapping. Understanding these fundamentals is vital to the success of fire suppression operations on the fireground. This includes knowing when and how to use air entrainment to your advantage, understanding when air entrainment can be your enemy, and understanding how to best apply the water through various application patterns, stream angles, and deflection methods to successfully coat and cool the surfaces of compartments and fuels inside a structure. In understanding the importance of air entrainment, we must first conceptualize how a water droplet moving through space entrains or draws in air. As you open the bail of the nozzle and the water begins to flow, the momentum of the hose stream propels these water droplets forward. As the droplets impact and compress the air ahead of them, an area of high pressure is created. In the wake of these droplets, there is now an area of low pressure, which causes surrounding air to be pulled in and carried forward with the droplet in an attempt to equalize the pressure. The air drawn in by these moving droplets is known as entrainment. If we visualize how many droplets make up a typical hose stream, you can see the potential magnitude of air entrainment depending on your stream type and application pattern. Suppose you are positioned at the start of a hallway, flowing a straight or solid stream aimed downrange in a fixed position with no manipulation. In this case, you are entraining about 1 to 2,000 cubic feet per minute of air into the stream. As soon as you start to manipulate the stream into an O pattern, for example, you increase the air entrained to about 4 to 6,000 cubic feet per minute. If we change the stream type to a narrow fog, the air entrainment increases dramatically. A narrow fog stream held fixed with no manipulation entrains approximately 10,000 cubic feet per minute of air. If that same narrow fog stream is now manipulated into an O pattern, the air entrainment continues to increase upwards of 15,000 cubic feet per minute. As the pattern changes from straight or solid to a narrow fog, the stream is now broken apart at the nozzle, which makes for more individual droplets at a smaller size. The more the stream is broken apart, and the more the stream is manipulated into a pattern, the more air is entrained. This increase will occur regardless of the type of pattern chosen. The amount of air entrained is also dependent on the speed in which you apply a given pattern rather than the specific flow and pressure of the system. It is important to note that the air entrainment in hose streams can be significant, dependent on the stream type and application pattern, and can reach or exceed the amount of air movement present with a positive pressure fan. Coupling the concepts of air entrainment in hose streams and the principles surrounding effective water mapping in structures will enable you to effectively apply water to maximize the potential survivability of trapped occupants and quickly suppress the fire. Surface cooling is vital to the success of extinguishment, stopping the heat absorption and subsequent re-radiation of the hot surfaces back into the compartment. Water mapping is understanding where your water goes and how it is distributed within a compartment to coat and cool surfaces. Learning how to employ different stream types, stream angles, application patterns, and methods of deflection will assist you in game time decision making to most effectively distribute water and map the surfaces inside of the compartment during suppression. First, let's look at how the angle in which the stream is applied will affect the distribution of water. If we apply a hose stream perpendicular to a surface, the water will radiate 360 degrees. We can see this applies both to a stream applied straight ahead towards a wall or a stream applied to the sealing surface of a compartment. The shallower the angle of the stream onto the sealing surface of the compartment, the more the water will be propelled forward towards whatever wall or obstruction is ahead of the nozzle firefighter. This does not provide any surface cooling to the ceiling or walls that make up the rest of the compartment. The steeper the angle into the compartment, the more the water will radiate outwards in all directions, providing better surface coverage and better cooling. As the stream hits the ceiling and the water radiates outward, the momentum and surface tension of the water carries it across the flat ceiling surface, common in most residential structures. Once the water has coated the ceiling surface and reaches the side walls of the compartment, it falls down these surfaces in sheets. As the water reaches the floor, it accumulates and pools in different areas. This water application method nearly simultaneously coats all surfaces within a compartment and is extremely effective in suppression. During suppression, initially employing a steep stream to coat all interior surfaces simultaneously will rapidly reduce temperatures inside the fire compartment. The drop in temperatures causes a drop in pressure and results in gas contraction, which improves conditions in the fire compartment and adjoining spaces. Coupling the concepts of air entrainment in hose streams and the principles surrounding effective water mapping in structures will enable you to effectively apply water to maximize the potential survivability of trapped occupants and quickly suppress the fire.